Assalamu alaikum dear students. I hope you're all fine by the grace of Almighty Allah. I welcome you all to the 19th lecture of Thermodynamics 2. Lecture 19. The contents of lecture 19 are Introduction to Exergy, Sources of Energy, Dead State of Thermodynamics, Available Energy referred to a cycle, Numerical Problems, and Conceptual Questions and Answer. So in this lecture we are starting the new chapter of Exergy. In your textbook this chapter is chapter number 10. So this is the continuation of the second law of thermodynamics. So as you know, the concept of available energy and the concept of wasteful energy arises from the second law of thermodynamics. So there are a couple of definitions. First we will go through them. So exergy is the available energy or availability of energy to perform maximum amount of work. So for example, we have recently studied the chapter of cyclic heat engines. So as you know that the Carnot heat engine is the reversible heat engine and it is the most efficient heat engine. So the efficiency of Carnot heat engine will always be greater than any other heat engine or actual heat engines or practical heat engines. Now if you install a Carnot heat engine between two thermal energy reservoirs, one is at the higher temperature and one is at the lower temperature. So one Carnot heat engine and one actual heat engine both have same two reservoirs, high and low temperature reservoirs. So as you know that the efficiency of Carnot heat engine will be the maximum efficiency and the work produced by the Carnot heat engine will be greater than the work produced by actual heat engine. So uh, that is some brief discussion. So as you can correspond it to with the exergy concept. So exergy is the available energy or availability of energy to perform maximum amount of work. So the sources of energy. So as you know that there are two main sources of energy, high grade energy, two forms of energy. One is high grade energy and the other is low grade energy. So high grade energy, we have mechanical or shaft work, electrical energy, kinetic energy, and water power. So mechanical or shaft work we have here turbine, etc. Electrical engine energy, the motion of electron. So usually in our home or appliances are worked at in the form the energy provided to the appliances in the form of electrical energy, kinetic energy due to the motion, and hydropower or water power energy. So all these energy relate to the high grade form of energy. And low grade form of energy, heat or thermal energy, heat derived from nuclear fission or heat derived from fossil fuels. So basically in the last chapter as well, when we were studying the entropy concept, I have already told you that work is a form of high grade energy and heat is a form of low grade form of energy. So here heat is derived from it is derived from fossil fuel combustion or thermal energy or nuclear fission or etc. But overall concept is that heat is a low grade form of energy. So work is a high grade form of energy and heat is a low grade form of energy. High grade form of energy is the total available energy. So let's suppose here we have four different, here we have 100 kilojoule of energy from high grade form of energy. So and here also we have 100 kilojoule of energy from low grade form of energy. So here you should remember that high grade form of energy like work, here we have entire 100 kilojoule of energy that we can use for work, but here less than 100 kilojoule of energy will be present, maybe 90%, 80%. So low grade form of energy is not altogether present for to perform our work. Some of that will be in the form of unavailable energy. So 100 kilojoule, maybe 80 kilojoule is available energy and 20 kilojoule will be unavailable energy. From second law of thermodynamics, this is the equation we have already studied. Heat is equal to work plus waste. Uh, we have studied that equation when we were discussing the cyclic heat engine, that the energy supplied to the engine from high temperature reservoir, some of that will be converted into work and the rest will be rejected into low temperature reservoir. So I will draw here, that is high temperature thermal energy reservoir. Heat is supplied to a heat engine, some of that will be converted into work and the rest will be rejected to low temperature thermal energy reservoir. So that is the waste and that is the useful energy. That is the useful. So the useful energy is termed as exergy. So the work produced useful is exergy and the wasteful energy is known as energy. So energy is referred here and exergy is produced by heat engine. Therefore, we can say that energy is the sum of exergy and energy. So energy is the summation of useful energy and wasteful energy. So useful energy is termed as exergy and wasteful energy is termed as energy. So here energy, you should remember the spelling is, it start from A, not E. So here energy is the total sum and it consists of a part that is useful, that is exergy, and the part that is not useful, that is energy. So exergy, that is the available energy. So the definition, the part of low grade energy which is available for conversion to high grade energy while following the second law of thermodynamics. So exergy is the useful part of low grade form of energy. For example, if you are asked what is the portion of exergy when we are discussing about electrical energy, then there is no portion of energy. 100% of electrical energy will be converted into work. So the 100% available energy is termed as exergy, and the value of exergy for electrical energy is 0 for energy, because 100% of electrical energy is available energy. Now energy, that is unavailable energy, the part of low grade energy which is not converted into high grade form of energy. So in the previous slide I have given you the example of heat engine, that a certain amount of heat is absorbed by the heat engine from high temperature thermal energy reservoir and some of that work will be produced, and that work will be termed as exergy, and rest of the energy that is rejected into the atmosphere or ambient is termed as energy or unavailable energy. Now there is a concept of dead state of thermodynamic system. So the definition of dead state of thermodynamic system is when a system comes in equilibrium to its surroundings, which means that the availability of the system is zero, then it is known as dead state. No useful work can be obtained from a system which is in dead state. So to explain it, let's suppose we have a body. So that is a body A, and it is at certain temperature T, and the let's suppose that it is a temperature 100 degrees centigrade, and the ambient temperature or the surrounding air have a temperature of 25 degrees centigrade. So heat will transfer from body to the surrounding. So as this is a finite body, so its temperature will reduce, whereas temperature of the surrounding will slightly increase, because usually we term ambient as a low temperature reservoir, therefore it is a condition of reservoir that its temperature does not change. So however, the temperature of body will reduce. So as the temperature of the body approaches 25 degrees centigrade, the heat transfer will slow down, and eventually at 25 degrees centigrade, when the temperature of body equals the temperature of surrounding, then the heat transfer will stop. So that condition, when the finite body temperature becomes equal to the temperature of surrounding, this is known as equilibrium state, and now no heat will transfer from body to the surrounding. So in thermodynamics term, this state is termed as dead state, because no work can be extruded with the body at that state. So no useful work can be obtained from a system which is in dead state. So in dead state, no work can be deducted out or obtained. So for example, atmosphere is considered as the dead state, because here I have given you example of the surrounding. So atmosphere is considered at the dead state, because if you put a heat engine in the atmosphere, because there is no temperature difference, so no useful work can be obtained by the heat engine. So at the dead state, the value of exergy is zero. We cannot get work from atmosphere. So the same I have told you. That state also provides the reference to any particular state of the system. So uh, it is a very important concept of dead state in thermodynamics, because uh, it is analogous it is analogous to the uh, frame of reference frame of reference. So the dead state provide the frame of reference for other thermodynamics. So here we have 100 degrees centigrade body, so dead state will provide a reference. For example, energy of state 1 is equal to state 1 energy minus dead state. So dead state here provide a reference to the thermodynamic system. So here more example of dead state system is given. Available energy, so exergy or available energy, usually denoted by symbol X, is the maximum useful energy. So the availability of given system is defined as the maximum useful work that can be obtained in the process in which system comes to equilibrium with surrounding or attain the dead state. So for example, here we have a state A. uh, at state A, there the body is at state A and it is at certain temperature T. So when it goes, it rejects that energy in the form of work. So here the temperature difference, we utilize that temperature difference to gain maximum amount of work, and the body temperature reduces and it reaches the dead state. So here state B is representing the dead state. So dead state provide a reference, so at a certain state how much maximum energy we can obtain, it is the difference of that energy of state with the dead state. So maximum energy of certain state that we can obtain is equal to energy at state A minus energy of dead state. So here we have two cases. So the case one is work producing devices. So it is a closed system and it's a reversible process. So here we have a piston cylinder system shown. So for work producing device, we have entered Q amount of heat. A certain working fluid, maybe a gas, is present in the piston cylinder system. So as Q amount of heat is supplied, then initially the piston cylinder is at state 1, and as the heat is entered into the system, the gas will expand, and now you see the piston moves up. W reversible or W amount of work is done on the piston due to the addition of heat into the system. So W work will be performed on the piston, and piston will move up to the state 2. So also you have to remember that as the atmospheric pressure is acting on the piston from outside, so the arrow representing the atmospheric pressure from upside, that is pushing inside the piston. So the reversible work is equal to useful work plus surrounding work. So that reversible work will have to face two forces. One is to uh, push that piston up, and the second one is to oppose the atmospheric pressure as well. So W reversible is greater than useful work, because it is useful work plus surrounding. So here some W surrounding is the work done by the atmospheric pressure. So W reversible is greater than useful work. And now for work consuming device. So it is a reverse of the above process. So it is also a closed and reversible process. So same amount. Now the piston cylinder is state 1, and the work reversible is introduced. So P atmospheric is pushing the piston down. So work is put into the system, and W reversible plus W surrounding is equal to useful work. So W reversible is acting into the system plus atmospheric pressure is pushing the system down. The piston is moving downside, and at state 2 the piston is moved, as you can see, is moved down. So at that state you see that useful work is now greater than reversible work. In the case 1, when the work producing device, the reversible work is greater than W useful, and in work consuming device, W useful is greater than W reversible. Now for case 3, it is for open system. So in open system, as you know, that there is an energy interaction as well the mass interaction. So open system means the fluid is moving, so mass is entering and leaving in the system. So a pipe diagram or schematic is shown, and certain mass flow rate is entering into the pipe and mass flow rate is exiting. So W surrounding is no work done on the surrounding in this time, because these are rigid bodies and the mass is flowing inside the pipe. So if you compare it with the previous example, that was a piston cylinder system and atmospheric pressure was exerting on the piston. Now there is no surrounding work. So W reversible plus W surrounding is W useful, that is the main equation, and as W surrounding is equal to 0, so W reversible is equal to W useful. So all the work on the fluid moving is equal to the W useful. So the concept of Carnot heat engine we have already studied that in the cyclic heat engine chapter. So TS diagram, we will not go into the details of the process involved in the Carnot heat engine. Rather, we will discuss that Carnot heat engine with the aspect of exergy. So TS diagram of Carnot heat engine, as you can see, uh, because these are four reversible process, two isothermal and two adiabatic process. So A, B and C, D are two isothermal process, and C, A and D, B are two reversible adiabatic or isentropic process. Now here, if we have given the TS diagram of Carnot heat engine, so here Q1 is W plus Q2, and Q1 is available energy plus unavailable energy. So in Carnot heat engine, Q1 is the amount of heat that is absorbed by heat engine from high temperature thermal energy reservoir. Some of that energy is converted into work, and Q2 is the amount of energy that is rejected by heat into the low temperature thermal energy reservoir. So the amount of heat supplied to the Carnot heat engine is equal to the work produced in the form of available energy plus Q2 that is rejected into the ambient, that is the unavailable energy. Now if you look at closely at the TS diagram, so the area A, B, C, D, so area inside the TS diagram process represent the available energy, whereas the area CDEF, CDEF is the area that is below the process. So the area CDEF represent the unavailable energy. So now if you have been given a TS diagram, and certain on the x and y axis the certain temperatures on the y-axis, and on the x-axis certain value of entropy are given to you, and you are asked to calculate the available energy and unavailable energy, then you just have to calculate the area. So here ABCD is a rectangle, so length into breadth or length into width is the area of rectangle. So here you can calculate the area of ABCD rectangle, that is available energy, and you can calculate the area of rectangle CDEF, that represent the value of unavailable energy. available energy referred to a cycle. So in the previous diagram, as you can know that the TS diagram of Carnot heat engine. So Carnot heat engine is a cyclic device. Because, so its TS diagram is shown here. So it represents the four reversible process, two isothermal and two adiabatic process. The area A, B, C, D represent the available energy, whereas the area C, D, E, F represent the unavailable energy. So here is the schematic diagram of heat engine. So a reservoir that is at temperature, certain temperature T. So heat engine is absorbing QH amount of heat from a reservoir that is at temperature T and producing W useful amount of work, whereas heat engine is rejecting Q naught amount of heat into the surrounding that is at a temperature T naught. So as we have discussed that the T naught or atmosphere or surrounding is termed as a dead state. So for dead state we usually represent the temperature with T naught and pressure P naught. So here are some calculation. So that is the same schematic that we have discussed. So high temperature reservoir is at temperature T, low temperature reservoir is at temperature T naught, and QH amount is of heat is absorbed from high temperature reservoir and Q naught amount of heat is ejected to the low temperature reservoir and W useful amount of work is produced. So here surrounding is at a dead state. So Q is equal to W useful plus Q naught. From first law of thermodynamics, so QH amount of heat is entering, Q naught is ejecting into the surrounding and W useful is produced. So W useful is equal to Q minus Q naught. From Carnot's second principle, so we have already studied the Carnot first and second principle. So Q by T is equal to Q naught by T naught. So QH over T is equal to Q naught divided by T naught. The ratio of heat, the ratio of heat with this ratio of heat that is coming out of the reservoir uh, divided by the temperature of the reservoir is equal to the ratio of heat that is absorbed by the low temperature reservoir divided by the temperature of low temperature reservoir is same. So it is, this relation is from Carnot's second principle. So Q naught is equal to Q by T, T naught. Q naught is the amount of heat that is rejected to the surrounding. So here we have Q naught, the first law of thermodynamics relation. So we will replace the value of Q naught by the help that relation we have obtained by the Carnot second principle. So W useful is equal to Q minus Q by T, T naught. So Q will be taken out common and we have a relation W useful is equal to Q into 1 minus T naught over T. So here you must remember that W useful is the value of exergy. So here available energy depends on total energy of the system Q. So QH is the total amount of energy that is entering into the system, that is a heat engine. The state of the system T. So the temperature T is the temperature of high temperature reservoir and state of surrounding. So available energy depend on the both temperature of system and surrounding and the content or total energy of the system, that is Q. So these three parameter of the system tell us how much available energy there is present in the system. So useful energy of cyclic process in terms of entropy. So up till now we have calculated two process. One is with the help of TS diagram. So if TS diagram is given to you and you have been asked to calculate the available energy and unavailable energy, so you can calculate it with the help of area. And in the previous slide we have find the relation of available energy. Now we will find the relation of useful energy of cyclic process in terms of entropy. So the relation of entropy is ds is equal to q naught by t naught. So this relation is we apply this relation of entropy when we are discussing about when we are talking about the reservoir, and when we will be talking about a finite body, then the relation of entropy is different. uh, but here in this case, as we have reservoir, so both reservoir, high temperature reservoir and low temperature reservoir, so here we will use the relation of entropy, that is ds is equal to q naught over t naught. So q naught is equal to t naught del s. Useful work is equal to q minus q naught. So W useful is q naught minus t naught delta S. So here W useful is also the value of exergy. So that is the third relation that we have found out to calculate the value of available energy, that is in term of entropy. So loss in available energy. So as you know that available energy and unavailable energy runs parallel to each other because they both combine. So available energy and unavailable energy both sum up to make the total form of energy. So as there is a loss in available energy or decrease in available energy, then on the other hand there will be an increase in unavailable energy. So decrease in available energy when heat is transferred through a finite temperature difference. Loss in available energy. So all three uh, uh, when there is written decrease in available energy, loss in available energy, or increase in unavailable energy, all these things means the same. And when we are talking about finite temperature difference, then it means we are talking about a body, so the temperature of body will reduce. So here two bodies are shown, one is at temperature T1 and other is at temperature T2. So consider a body as shown. So here a body is shown. Let the initial temperature of body is T1. So T1 a body is initially as temperature T1. So you may give that a number of 100 degrees centigrade, and at this temperature the available energy is available energy 1. So at state 1 the temperature of body 1 is T1, and at that temperature the value of content of available energy for body is AE1. So some of the heat is ejected from body and the temperature of body is reduced to T2. So Q amount of energy from body is rejected to the atmosphere and the temperature of body is reduced, and now the temperature is T2. For example, let the temperature of T1 is equal to 100 degrees centigrade. A certain amount of heat is ejected to the surrounding. Now the temperature of body is 80 degrees centigrade. And at this temperature of T2, the available energy of the body is AE2. So at 80 degrees centigrade, the available energy of the body is AE2. So AE1 is greater than AE2 because T1 is greater than T2. So here a reservoir T1 is shown and Q amount of energy is entered into the heat engine. W useful is the amount work that is produced by heat engine, that is the available energy 1, and Q naught is the amount of unavailable energy, and Q naught is the amount of heat rejected from heat engine into the surrounding, that is at a dead state. Now for case 1, when temperature is T1, so at T1 the temperature is T1 and the available energy is AE1. So here Q is the total amount of energy, AE1 is the available amount of energy, and Q naught is the unavailable energy. So for case 1 the available energy is AE1. Now case 2, so here you see that the certain amount of energy is lost to the ambient and Q amount of energy that is entered into the heat engine, but now the temperature is reduced. So for example, in the last slide the temperature of reservoir is 100 degrees centigrade, from which the heat is entered into the heat engine. So now the temperature of T2 reservoir is 80 degrees centigrade and Q amount of heat, the same amount of heat is entered into the heat engine. Now Q is the total amount of energy, and for case 2 the available energy is AE2 and Q naught is the amount of energy that is rejected into the surrounding. So now we will discuss some conceptual question answer. Can we have any energy transfer as heat transfer that is 100% available? So the possible amount of work that can be obtained equal to exergy or availability. So as you know that exergy is the maximum amount of work that can be obtained. The maximum is limited to that, or if the reversible heat engine, if we have a reversible heat engine and we have an actual heat engine, then the maximum amount of work that can be produced by a reversible heat engine is the amount of exergy or availability that we can achieve from any system. So when we are transferring energy in the form of heat, so 100% energy is not available because the formula is 1 minus T naught over T into Q. So to get the 100% efficiency, we have to uh, produce an infinite amount of high temperature in the high temperature thermal energy reservoir, which is not possible. Therefore, to transfer 100% available energy is not possible. Its electrical work is 100% available. So yes, electrical energy is a high grade form of energy and it has 100% exergy or availability. So electrical work is 100% available. So in the last slide, heat transfer or heat energy is not 100% available, and in the current slide electrical work is 100% available. A nozzle does not have any actual work involved. How should you then interpret the reversible work? So here we have been asked that how you will represent a reversible work when the fluid is flowing through within the nozzle. So the purpose of nozzle is not to make work but to increase the velocity, because you know that the function of nozzle is to increase velocity and decrease pressure. So here the answer suggests that the function of nozzle is not to produce work but to increase the velocity or kinetic energy. Hence, reversible, if we are talking about the reversible nozzle, then the energy or kinetic energy produced within the nozzle or increase in the velocity will compensate the reversible work. So let's suppose we have two form of nozzle, and we have two nozzle, one is an actual nozzle and one is a reversible nozzle. So if the exit will for same initial inlet condition, the exit velocity of actual nozzle is 25 meter per second, then the exit velocity of reversible nozzle will be greater than 25, and the reversible work will be equal to the possible total kinetic energy output of the reversible nozzle. If an actual control volume process is reversible, what can you say about the work done? So the work term is maximum possible. If the work is positive, then it is maximum possible work out, and if the work is negative, so it is a minimum work possible that must be supplied. Can entropy change in control volume process that is reversible? So yes, it can. A flow in or out of the state with a different entropy than the average entropy inside or heat transfer will change the entropy. All the terms that changes the entropy are transfer terms, so there is no net increase or generation of entropy. So here you know that for the reversible there is no entropy generation, and the entropy for control volume work can be changed because the for different state the heat will be transferred, that will change the entropy, but the overall entropy will remain constant, and there will be no increase or addition or entropy generation term due to the reversible process. Energy can be stored as internal energy, potential energy, kinetic energy. Are those energy forms of 100% available? So here we have been asked about internal energy, potential energy, and kinetic energy. The internal energy is only partly available. A process like an expansion van give out work, or if it cools by heat transfer out, it is a Q out that is only partly available as work. So as you know that the internal energy is really the function of heat or work that is added or reduced by the system. So the internal energy is not 100% available, only partly available. Now we are talking about potential and kinetic energy, then these form of energy is approximately 100% available. So if we are talking about potential energy, then a compressed spring or gravitation potential energy or charged battery uh, have availability of 100% available work. And kinetic energy, usually kinetic energy is available in the form of motion, different component are moving, so it is also 100% available, but there is certain amount that is reduced due to the frictional effect, or depend about the losses that depend upon the mechanical component that are used in the system. So kinetic and potential energies are 100% approximately available, and internal energy is partly available. Home assignment of lecture 19. All students are advised to go through example problem of each topic discussed in this lecture, and all students must submit handwritten lecture summary report, and you are advised to make a lecture summary report and mail it to my email id, that is darsalan@ciitwa.edu.pk, and you must prepare this lecture thoroughly. So if you are asked question answer in the next in the online question answer session, then you are able to answer these questions. Thank you very much. Take care. Allah Hafiz.